Okay, this video is about calculating the delta T. If you look at these equations, delta TB is for the change in boiling temperature. Boiling point goes up when you add a solute to water. It's usually water. In the equation, this Kb is just a constant, and then M is for molarity of the ions or whatever it is that you have that you're dissolving. The similar equation over here, delta TF for freezing, is once you figure this out, that's how much lower it'll freeze than what it normally freezes. So when you, once you have delta TF, if you want to know like the new freezing point of the solution, you would take, the normal freezing point, 0, and then you're going to subtract whatever you get for TF. And then if you want to know the new boiling point of the solution, you would take the normal boiling point of water, 100 degrees Celsius, and then you would add whatever you get when you solve for delta TB. So these problems here, we have to always look at what's dissolving. So in this case, it's the calcium chloride in water, just means that it dissolves in water. So it's going to break up into calcium, 1 calcium ion for every 2 chloride ions. And then I know that it's a 3.1 molar or moles per liter of calcium chloride. So this is in a 1-to-1 ratio. So this is going to be 3.1 moles then per liter of calcium ions, and then multiplied by 2 because there's twice as many moles of chloride. So it would be 6.2 molarity of chloride ions. So the total molarity then of the ions is going to be 9.3 moles of ions per liter. This is gone. It breaks up into this. So now we can plug in and calculate the delta TB for boiling first. So delta TB is going to equal the Kb, which is 0.52 Celsius per molarity, times my molarity of my particles in the solution. So times 9.3 molarity. So then I get a change in boiling temperature of 4.8 degrees Celsius. So then my new boiling point, which is what they're looking for, the boiling point of the solution, is going to equal normal boiling point of just pure water plus that 4.8. So it'll be 104.8 Celsius. Here's another problem, and this is a freezing point problem. Again, you have a certain molarity of, in this case, sodium chloride. So we would want to break that up because in water it breaks into these ions. And if it was 2 moles per liter of sodium chloride to start with, then I got 2 moles per liter of sodium and 2 moles per liter of the chloride ions. This is gone. So I have a total of 4 moles per liter of particles. So when I calculate the freezing point, I first of all have to get delta TF. So how much is that temperature going to change? Delta is changing. So I'm going to take that freezing point constant for water. Everything has its own constant. We'll be dealing with water times the molarity of the solution. So the 1.85 Celsius per molarity is the constant that we use for freezing, and then multiply that by the molarity of the ions, which we just figured out over here. So when I do this, my molarities cancel, and I end up with 7.4 degrees Celsius. So my new freezing point is going to be the old freezing point, 0, minus that 7.4 So it'll be negative 7.4 degrees Celsius. So the freezing point is lower than the normal, so I subtract. The boiling point is higher than the normal, so I add.